Back to illuminance measurements again. So just a few words. Most of you already know, but Saint-Gobain is producing materials, and particularly many building materials. And it's naturally interested to understand what is their influence on occupants' comfort. But in order to do that, we first need to understand what is a comfortable room, how we can assess comfort, measure it, and then later also how to make it better. So this is why in our R&D programs we have several studies dealing with various types of comfort, including visual comfort. And in particular, we are interested in the topic of daylight, as it is one of the most important factors on occupants' comfort and well-being. And what we realized is that it actually turns out to be quite difficult to do post-occupant studies and evaluate real performance of a building with respect to daylight availability. Why? Well, because it depends on many external variable elements, such as external luminance levels, also window characteristics, which are both glazing types, but also shape, position. Then occupant behavior, also external elements that can change with season, for example, the canopies of the trees, or interior layout. So taking all this into account, there is actually a big gap between predicted performance and the real performance in these terms. And what are the tools that we have to evaluate daylight availability? Well, basically, we have one option, simulation, and then one option are basically point, time, space measurements. From those, we typically calculate metrics that are well-defined in the standards, and then we thought, okay, if they're well-defined, then in practice this is exactly what people do. But actually in practice is not that simple at all. We had several opportunities, particularly one where we were accompanying one big engineering studio to evaluate various comforts in our new headquarter building near Paris. And we realized that in practice it's actually quite hard to perform these measurements as they are defined. So for example, daylight factor measurements, it was almost impossible to find the date with overcast sky, but that it's not raining, so that you can use your instruments. We realized that engineering studio, with all the constraints that they have and all the things that they need to do in a day, they were not actually doing simultaneous measurements inside and outside. So I mean, to our view, it was quite complicated. And it's not much easier with simulations. Nowadays, it's true that there are very good tools in terms of computational speed. But still, if you want to have good accuracy with simulation, you need a very detailed 3D model. And you need good information about optical properties of all the materials, both outside and inside. And engineering studios, on everyday basis, they typically really don't have this information, unfortunately. So what we realized then, there are several proposals in the literature how to overcome some of these difficulties. But for us, the motivation was really to make something that is very practical on everyday basis, that is easy to use, but that give us somehow sufficient accuracy in estimating particularly yearly metrics, as you will see. And for the proposal that I'm going to present, we were still quite inspired by what already exists in the literature. So we were inspired first by the LEED standard, which basically said it's better to measure 2 times and not only 1 time. So it proposes if you do a first measurement in certain month, to do a second one, to repeat it in a different time of the year. And then there is this interesting publication, which is actually on simulations. And it was made back at the time when it was still computationally hard to even calculate all the luminance for every day in a year. So what they proposed is to take 5 random days in each month and then do the calculation, for example, daylight autonomy only on these days. And they actually got good values with errors around 5%. So we wanted to propose something like that, but we cannot directly transpose this proposal because we cannot measure random days. It would be too complicated as a procedure, right? So what we are going to do, as you will see, is to propose several measurements in a year that last for a bit more days, and then the question is how long and how many of these measurements, and we will get to that. Then another important thing is then how are we in practice going to measure? If we want to characterize the whole space, are we going to do it with lux meters, wired ones? It's going to be quite complicated. But luckily, we have a better proposal, and there is a tool that we developed internally in Saint-Gobain Research Paris that we call MC Luxbox Kit, and which allows to measure illuminance levels in several points in space using these wireless detectors. And we can measure for a prolonged time, so this can easily be a few days or even weeks, or if you have nothing against still changing batteries, then you can even do the whole year. But again, we don't want to propose a protocol that measures every day of the year, because for the occupants that would be not that convenient. But in any case, we were wondering, okay, we have this tool, and how can we use it also to somehow estimate yearly metrics without actually measuring every day of the year. The idea is then to use these direct measurements for measuring several days, and that allows us, as I mentioned, to then really take real values that automatically take into account all the geometries, materials, even shade use. We will have everything in the measurement. And what we can do is to define what I call short-term daylight autonomy and short-term spatial daylight autonomy, which are defined in a similar way as the standard ones. But instead of applying thresholds for every hour of every day in a year, we will apply thresholds on measurements in the days that we measured. With the detectors, we can have a resolution of measurement of what we want, so it can be 10 minutes, an hour. We set it typically to an hour, as it's traditionally done. Before continuing, just to mention that we are aware of the existence of this somehow similar proposal from some time ago that also mentioned a few measurements in the year. However, as you will see, doesn't take into account different climates, and also doesn't calculate these same metrics. So I want to point out that it's still not the same. Okay, so you remember that we mentioned at the very beginning then that one of the main factors that influence daylight availability in the room is external daylight availability. And it's this parameter that is going to tell us how many times in the year we want to repeat the measurement. External daylight availability depends on geography, depends on climate of certain regions. So this is why we first took a look into just data of global external horizontal illuminance. And we use this data to try to understand how many times in a year we need to measure. So what happens is that, as I mentioned, you have different situations for different geographies. Sometimes you seem to have external luminances which are very close by or that are very spread out. For example, in France, you will have big changes and you will have four seasons. So now we wanted to cluster this data in a way to decide how many measurements per year we will have. And our criteria at the end is practicality. So we want to take as many measurements possible to capture all the differences, but still be quite practical and not repeat too many times. And we see that we can cluster these external illuminants. It just cannot always be the same. We don't have the same thresholds that are universal for all geographies, but we can still distinguish different groups or seasons for each of these localizations. So this allows us to first identify for each localization how many times we will measure. So it will be 4 times for example, Rouen or Svalbard, or 2 times for Miami. Okay. So next thing we need to answer is still, okay, if we do that, still how long we need to measure, how many days, and do we get any reasonable error? And in order to examine this, it would be very hard to do it with measurements, right? Because it would be hard to have one same building in many places in the world with different orientations. So as a proof of concept, we use simulation. That is one building in 3D model in Rhino and coupled with Climate Studio. And in our case, it is not important that absolute values are corresponding to something in reality, but that we can look in a relative. Okay, and this allows us really to explore all different scenarios, lengths, orientations, and to come to the final proposal, which is to do 2 weeks measurements as many times as there are seasons. And I will present you some of the typical results that we have. So this is for Rouen, north orientation, a map of daylight autonomy, and map of a difference of standard versus short-term daylight autonomy, taking 4 seasons and 15 days. So here you see that the error is quite small, particularly small for parts that have lower daylight autonomy or very high, and slightly bigger for these intermediate values. And here is the proof, right, for this localization. Taking only 2 seasons, it's not that great. We get much bigger errors than taking 4 seasons. So this is typical result for daylight autonomy. It's also interesting to look spatial daylight autonomy, and it's very practical because now it's only a number. We don't have a map, but number, and then I can present you one graph like that. There's quite some information here. So first, we have 2 localization, Miami and Rouen, and for each of them, you have different orientations, and you have a different length of measuring campaigns. So here what you can see, first of all, for different orientations, result changes but not dramatically. And then also with the days, it drops, but again between 25 days and 15 days, it's not that big. So this is why we propose to keep it at 15 days. Okay, and here just to say, I say average delta, because I actually average over all possible different choices of 5 days that I'm taking, because I can take different days into account. So here was just a table with some more climates, that is SDA values, and then how SDA changes with the number of days. And finally, some few conclusions. Performing 2 weeks measurement several times by year following the number of seasons allows to estimate yearly climate-based metrics. Result is quite independent on orientation and robust for both daylight autonomy and spatial daylight autonomy. Next step for us is to examine real data. We actually place some detectors to really measure throughout the year, so to really prove the point. But it's not the proposal we want to make. The idea is to prove even with the real data. And also we can go a bit further and also examine some other localizations. So thank you very much, and I hope to get your questions later.